actually checked. I'm not sure the rooms are actually posted, but the information about the test. And in particular, you need to go there if you have a course conflict. So we're going to ask you if you have a conflict with the test to complete a survey so we can help accommodate you at a time when you can write the test. Also, make sure you're getting help. So we have the instructor office hours, and one of them is always after this class. So that's a great opportunity. Make sure that if you have any questions about your lab reports, that you get those answered. We also have a ton of peer tutoring hours. And I would say in particular, if you're coming to instructor student hours, but you want somebody to spend a more individualized approach, look at your calculations, questions about using your calculator, questions about algebra, things like that. Sometimes that's really hard to access when you're in office hours when there's a lot of people, but the peer tutors are often underutilized and they are a great resource and can often provide a little bit more one-on-one support. So I really suggest that you check those out. And finally, if you want this 1% bonus at the end of the semester, I would suggest going on and completing the EDI modules before the end of the day tomorrow. And finally, always what we want to see is that you're doing the practice problems, okay? Chemistry is best learned by doing. So it's very important that you practice those problems. Okay, so now this is one of my favorite cartoons, which is Goldilocks. So Goldilocks is coming in here and she's looking at Daddy Bear's bowl and she's like, that oatmeal is too hot. But Mommy Bear's bowl, which is the medium bowl, is too cold. And the small bowl is just right. And she's saying, this doesn't make any sense. Goes against all the thermodynamics I have ever learned. And I like that because this is sort of getting at this idea of when properties are extensive, right? So those we made a big pot of oatmeal, and all of that oatmeal has the same heat capacity, right? The same ability to hold heat per unit amount per degree temperature, right? It takes a certain amount of energy to heat up a gram of oatmeal for one degree Celsius, right? And so the issue here is we take that oatmeal, it's all piping hot, we give a lot to Daddy Bear, right? We give a medium amount to Mommy Bear and a small amount to Baby Bear. Well, the thing is, whose would be cold? Whose would be the coldest, right? Because the heat capacity of the oatmeal is an intensive property, right? It doesn't change with the amount there, but the actual amount of heat stored in each of those oatmeal samples is different, and the smaller sample would have overall less heat. And so, if the dissipation of heat was equal, the smaller sample, Baby Bear's oatmeal, should be the coldest. Right. So it really goes against everything we learned, but we don't know. Maybe we warmed up Baby Bears at the end and that's why it was just right. Okay, so we're going to finish up our discussion of enthalpy here and our discussion of thermochemistry. And I did want to remind everybody that unfortunately it is my last class today with you. Now, luckily, a couple of good things. Professor DeBakir will be here on Thursday with you to start the kinetics unit. But because this is my last lecture, this is the last content that will be covered on term test 1. So that's useful to know when that ends. And so it's this lecture going on to tutorial number 4. And then actually tutorial number 5 will be some practice for the term test itself. Now, the other good thing is that I'll be in office hours next week to make sure that, if you have any questions about the term test content, that I'm here to answer those. If you have questions about the new content, I always love talking about kinetics, so I also welcome that. And finally, as I've mentioned before, I'm going to be back for Chemistry 135, so we will be reunited again, and that will be fantastic. I also wanted to mention that you guys have been a fantastic class, and I've really enjoyed being here with you, really, really a lot, and that I think you're all going to do fantastic. That you have really been invested in the content, you're engaging with it actively, and I think you're really setting yourself up for success. And so just make sure you continue with those practice problems and asking for any help that you need. Okay, so let's talk about the content today. So we're going to start off today talking about some of the rules. Okay, so I'm a person that likes rules. I like rules, especially with things like recycling. I don't know how useful recycling is in truth, but I love following things like recycling rules. And so we have some important rules here when we're talking about enthalpy, and these will build on some of the things that we've already talked about. So our first rule is that the sign of our enthalpy indicates the direction of heat flow. And this is sort of a convention that many of us are used to. So in a thermochemical equation here, where we have an enthalpy associated with an equation, if that enthalpy value is negative, that means that when the reaction proceeds, heat is lost, right? And the surroundings are increase in temperature. And if our enthalpy is positive, that means heat comes into the reaction. And so our surroundings or our solution decrease in temperature. Okay, so they get colder. All right. The other thing is that since enthalpy is a state function, if we reverse the direction of our reaction, then we change the sign of our enthalpy. So the idea here being if our reaction is exothermic in one direction, if we reverse it, it will be endothermic in the other direction and the same amount, the same because enthalpy is a state function, right? We're going from higher energy to lower energy, so we were releasing energy, or we're going from lower energy to higher energy. Energy is coming into the system, okay? But they're the same magnitude. Okay, now because enthalpy is an extensive function, what that means is if we modify our reaction, we have to modify the enthalpy that's associated with it. So this is a time for me to sort of emphasize something, which is that enthalpy and enthalpy change is always associated with a specific reaction. We don't just have this like general enthalpy, right? The enthalpy is 500, 100. It's not like that. It's always associated with a very specific reaction, right? So here we have propane being combusted in the presence of oxygen gas to give us CO2 and water. And this is the enthalpy value for this reaction. Change direction, it's positive. And if now up here we had 1 mole of propane, if we multiply the whole reaction by 2, so now we end up with 2 moles of propane, 10 of oxygen, 6 and 8, we multiply our enthalpy by the same factor. Okay, and this is because enthalpy is an extensive property, meaning it does depend on how much is there. And so if we modify what is represented in our chemical equation, we need to modify the enthalpy that's associated with that reaction. Okay, now we do have this interesting question about the units of enthalpy. So you may have experienced before or seen in other resources, as is common, that enthalpy is represented simply as joules or kilojoules and not kilojoules per mole. Now we feel strongly about keeping that per mole unit, but we need to make sure that we understand what per mole means. So the per mole component of our enthalpy, as joules per mole or kilojoules per mole, refers to the moles of reactants and products as defined by the associated balanced chemical equation. So that means here that this amount of heat, this negative 4438, 4,438 kilojoules per mole, is per 2 moles of propane, right? And up here, this was per 1 mole of propane. This is per 10 moles of oxygen consumed or per 6 moles of CO2 produced. Okay, so that per mole unit refers very specifically to the balanced chemical equation associated with that enthalpy value. And we'll practice this in another question. Okay, so another thing to keep in mind is that enthalpy does change with physical state because we know that enthalpy not only represents the forming and breaking of chemical bonds, but also the forming and breaking of intermolecular forces. So you do need to be careful. Like here we have the enthalpy associated with liquid water. If we were to change this to gas phase water, then the associated enthalpy would be different. So overall, to be entirely correct, we do need to specify phase when we're talking about enthalpy in these thermochemical reactions. Okay, so let's go ahead and work on this question and we'll see if we have any questions. So here, this is asking for the enthalpy change, the delta H for this reaction here. And you're to use this balanced thermochemical equation to calculate what the enthalpy change would be for this reaction. Okay, so go ahead and do this calculation and tell me whether you get A, B, C, D, or E in the chat. And while you're doing that, I'll just come to Hiba and see if we have any questions that have come out in the chat to you.
Yes. So when you say enthalpy is for a specific reaction, do you mean enthalpy values are unique to a specific reaction, which like two reactions will not have the same enthalpy?
Well, it's never impossible that two reactions would have the same enthalpy, but that an enthalpy value is always associated with a reaction. So it's always associated with a specific reaction with specific stoichiometry that has to be balanced. I hope that's answering the question.
Another one is how do you choose which reactant product to base it on?
No, you don't. You don't. That's a great question. How do you choose which one to base it on? It's true for all of them, right? So like here, let's do up here. This enthalpy is negative. Oh, I'm going to switch to blue. I like blue better. Is negative 2,219 kilojoules per 1 mole of propane, H8, that's gas, but it is negative 2,219 kilojoules of heat energy per 5 moles of O2. So they're all true, right? They're all true at the same time. It depends on what reactant or product you are interested in talking about. You don't base it on it's true for all of them. And it's per 3 moles of CO2 produced, per 4 moles of water produced. That's a great question. Is there one more, Hiba?
Yeah. Is delta E equal minus QV and delta H equal minus QP? So I believe there is a difference between provided notes and what was said in the last lecture.
Oh, sorry. Yeah, I can't follow what you said though, Hiba. Can you say it again?
Yeah, so like the question is the change in the energy is equal minus QV and
Equals
the
minus QV. Oh, you're talking about work is equal to minus P delta V.
like the question mentioned like delta E, but like maybe and
I
like the
think,
delta yeah.
yeah. I think we might have to deal with this in office hours. Yeah, because I can't quite get it. So maybe you can try to tell me again after the class and we can try to sort it out. Okay, let's keep going. Or if it's not clear, somebody can ask me then too, because I want to make sure all these questions are answered. Okay, but now let's answer this question, which is what is the enthalpy change for this particular reaction? So something we might notice is we have nitrogen dioxide over here in the reactants, but in this reaction here, it's in the products, right? So one thing we have to do is we have to reverse the reaction, right? So if we reverse the reaction, then what we end up with is changing the sign, right? So now we would have negative 66 kilojoules per mole, but we also see that our stoichiometry is not exactly right. This is only 1 mole of NO2, and this is 2 moles. So we would have to multiply the reaction by a half, meaning we have to divide all of the stoichiometries by 2. So we have 1/2 N2 gas plus 1 mole of O2 gas. And so then we would also have to multiply our enthalpy by 1/2. And this gives us our value of negative 33 kilojoules per mole. And that is answer A. So good job to everybody who answered A. And if you didn't answer A, then now maybe you've seen if there's something different that you would have done to my approach and your approach. Okay, so let's try another question. So the next question relates to this thermite reaction, which is the reaction of aluminum with chlorine gas. So here we have a flask that's filled with chlorine gas. And when we add our solid aluminum to it, it's a little bit choppy. Sorry about that. We add our aluminum to it. We see that we have this very exothermic reaction, right? We have a lot of energy out. And I think many of us have seen these type of exothermic reactions before because we've seen fire, right? So when we have a fire, that is an exothermic reaction and we can feel the energy and the heat produced that we feel with heat. And even some of it we can see with visible light. Okay. So the question here is how much heat in kilojoules is released if we fully react 5 grams of solid aluminum metal with chlorine gas? So in this case, we do have to know that our aluminum has an atomic mass of 27 grams per mole, right? And so I want you to give this question a try. Take a minute to give it a try. How would you answer this question, right? And I guess as a sort of to sort of think about the thought process we can use, we can remember that the heat evolved or consumed by a reaction is going to be equal to the number of moles that reacted times the enthalpy change of our reaction. Remember, this was an equation we used to calculate delta H from the heat, from the Q, from the heat given off by a reaction. Now we're sort of using it in the opposite way. How much heat is evolved if we understand how much is evolved per mole of the balanced equation, and we know how much is reacted. Okay? And somebody's asking me, how can we know it's releasing energy? Well, because the enthalpy is negative. Okay. So see if you can answer that question for a minute, and then we'll continue on. Hiba, is there a question that maybe I should address while we're working on this problem?
Yeah, just one related to the previous question. Why
Sure.
did you multiply by half?
Well, I multiplied by half because the stoichiometry matters, right? So this stoichiometry is not the same as this one, right? This is a 2, and this is, right, there's a 2, a 1. I reversed it. There's still a 2, 1, 2, but this is actually 1, 1/2, 1. So I have to multiply it by a half in order to represent the enthalpy change of this specific reaction. The stoichiometry matters. Yeah. Is there any additional questions?
No?
Okay. All right. So give this question a try. A couple of people have told me their answer in the chat, but I'm sure it might take a little bit of time. Okay. So let's just start this thought process together here. If you get your answer, you can give it to me in the chat so you're locked in and you know what you would have answered on your test. Okay. And no pressure if it's different, right? That's good. Just lock in your answer. Okay. And if not, then keep going and follow along with me here. So first of all, our number of moles of aluminum. So when I do number of moles, I really like to just use my units, but obviously we can also remember that number of moles is mass divided by molecular weight. But I like to always just say, okay, I have 5 grams of aluminum, and then I remember, well, there's 27 grams of aluminum to 1 mole of aluminum. So I have to divide, right? So I have 5 divided by 27, and this tells me I have 0.185 moles of aluminum. Okay, so now using this relationship here and also thinking about my units, I can see that N, the number of moles that reacted here, is 0.185 moles of aluminum because I'm told that I react it fully. So chlorine gas must be in excess. And I have to multiply that by my enthalpy. So my enthalpy is negative 1,408.4 kilojoules per how many moles of aluminum? Per 2 moles of aluminum. Because that is how many moles of aluminum is consumed in my balanced chemical equation. So this would then give me a Q, a heat released of negative 130 kilojoules. Now, we remember that the heat isn't really negative or positive, right? This is the same as thinking about whether a photon has been absorbed or a photon has been emitted. We're thinking about the change in energy of the system. Q being negative means that 130 kilojoules of heat energy has been released, right? If it was positive, that means it would have been consumed by the system because this is the Q of our system or Q of our reaction, right? Because our reaction is our system. Okay, is there any follow-up questions at this point, Hiba?
Yeah, I got one.
Mm-hmm.
So is not the enthalpy the same for the whole reaction regardless of the coefficient?
Yes, but that's what this per mole unit is, right? So the reason we're using the 2 for the aluminum is because the aluminum is a limiting reactant, we're told here, and it's determining how much heat is released. So if we were told instead how many moles of chlorine were consumed, then we would have X moles of chlorine gas, right? And we would have the same enthalpy value, but per 3 moles of Cl2. And then, or if we were told how much of the product, we were told how much of the product is produced, or if it was a limiting reactant problem and we needed to calculate which was limiting, and we did that by calculating the amount of product. We can also use per 2 moles. In this case, our product has a stoichiometry of 2. So this mole unit on the bottom of the enthalpy always has to include the stoichiometric coefficient in front of whatever species it is. Okay, so it is differently applied to each of these species within the balanced chemical equation. Is there a follow-up question? This is a confusing topic in a bit, right? It takes some getting used to. Hiba, is there any other questions that we should maybe discuss?
Yeah, I still get like a couple of questions related to why we divide by 2.
Yeah, I mean, there really isn't anything else to say, to be honest. We have to use it's not per 1 mole. That's why some people just omit the mole. It's not per 1 mole. It's per mole as defined by the balanced equation. So the reason there's a 2 here is because there's a 2 in front of the aluminum. So again, when you talk about mole, this mole has to be defined. What are you talking about? It has to be defined relative to one of the reactants or products. Sometimes everything has a stoichiometry of 1 and it's easy, right? But not in this case. Okay, so let's keep going. There may be other questions that come up. This is definitely something that we need to get used to. Okay, so we have an application of the fact that delta H is a state function. And this also actually relates to the fact that it's an extensive property, and that is Hess's law. So Hess's law tells us that we can add chemical equations and determine the enthalpy change by adding several steps. We can determine the total enthalpy change. Okay, let me slow down because I'm kind of tripping over my words. So our example here, we're using a similar type of diagram that we used to use for energy levels in the hydrogen atom, right? The lower they are, the lower in energy. When we're going up, our y-axis is increasing in energy. So now our energy in this figure is defined by enthalpy, but enthalpy is a type of energy. So here we have this idea that we're reacting solid carbon with O2 gas and producing carbon dioxide. So we can write a thermochemical equation that has carbon and O2 going directly to CO2, and it would have an enthalpy change here of negative 394 kilojoules per mole. But in that same process, instead of going directly, we could have carbon and O2 first reacting to give us carbon monoxide, and then this carbon monoxide reacting with another molecule of O2 to give us CO2. And so the idea here is if we can add two equations to get to the final equation, and in the process we can add the enthalpy values, and that is really directly related to the fact that enthalpy is a state function. So let's do an example here. I think the easiest way to sort of think about this is to do an example. And so this example talks about the solvent methylene chloride, which is dichloromethane, and it can be prepared by reacting methane with chlorine. So we want to know the delta H value here for the reaction of methane with 2 moles of chlorine gas to give us dichloromethane gas and HCl gas. Okay, so, and the information that we've been given in order to do this reaction is the enthalpy change for methane reacting with 1 mole to give us chloromethane and 1 mole of HCl, and then chloromethane reacting with another mole of chlorine gas to give us dichloromethane and HCl. So the idea here is that we can basically add these equations in the same way that we would add mathematical equations. So I see here I have methane as a reactant, and I don't have any methane on the product side. So methane stays here as a product for me. And I also, stays here as a reactant. Sorry about that. And here I have 2 moles of chlorine gas that are reactants. So I'm going to add those together and say I have in this total overall reaction, this is an overall reaction built on 2 different steps. I have 2 moles of chlorine gas. Now, the last thing I have over here on the reactant side is chloromethane. Well, I also have chloromethane on the product side. And so since it's on the products and the reactant side, it doesn't change during the reaction. And so I can cancel it out. And then on this side, I still have my dichloromethane, and I have 2 moles of HCl gas. So if I add these 2 equations to give me this overall equation, how do I handle their enthalpy values? Well, like we said on the last slide, we would add them together. So we would take negative 98.3 kilojoules per mole plus the enthalpy of the other reaction, which is 104 kilojoules per mole, giving me an overall enthalpy change of negative 202 kilojoules per mole. Now, remember, if you wanted to, so in this case, we're sort of directly adding them. You can, in essence, subtract one. And what that would really mean was before you do the addition, you swap the sides. Because again, we remember one of our rules is if we take the opposite enthalpy, we're switching the reactants. We're going in the opposite direction. So reactants become products and products become reactants. Okay, so we can, if we have thermochemical data on our steps and we want the thermochemical data on our products, we can actually simply add those chemical equations to get there. Are there any questions that have come your way about this, Hiba?
Yes, so can we do these to every equation?
Yes. Yep, we can. Any other questions?
I think no.
Okay, good. Okay,
Yeah.
so this is really neat, Hess's law, that we can add, if we can add reactions, we can add their resulting enthalpies. And so this sort of leads us to the fact that this is a very useful thing to explore, but in order to actually do it properly, we need to keep some things in mind. So one of the things we need to keep in mind is that our enthalpy values will change with states, right? Whether we have a liquid or a solid, they'll also change with temperature, they'll change with pressure. And so we need something that sort of controls for all of these components. And that is something we call standard state. So standard state, if it's a pure substance, then we're talking about its most stable form at 1 atmosphere and 25 degrees, right? So this is like hydrogen gas for hydrogen. This is like things like that in their pure form, carbon is a solid, iron, most metals are solids. And if we are defining something as a gas, or if it is a gas, right, in its most pure form, then the gas will be at a pressure of 1 atmosphere. It will be behaving ideally. And again, in our cases, it will be at 25 degrees. We say this usually here because there's a few different times where standard state is defined at 0 degrees Celsius. But for our purposes in this class, we will define it always at 25 degrees. But we're just saying usually because we are recognizing that sometimes in certain cases it's defined at 0. But for us, we will define it at 25 degrees. And if we're talking about something in solution, right, we do a lot of reactions that are in an aqueous solution, then if something is at standard state, it has to be at 1 mole per liter concentration, and again at 25 degrees Celsius. And so if something is at standard state, meaning this equation represents constituents at standard state, we add a special knot onto that our thermodynamic property. Okay, that's what that little knot means. It means that all of our constituents within the reaction are at standard state as defined on this slide. So the other thing I wanted to mention here is we're thinking about tables of values that we can look up. Well, there are tables of values we can use, and those are called standard enthalpies of formation. So standard enthalpies of formation are reference values where because again, our enthalpy values always have to be related to a reaction. So when we're looking something up, we can't just look up the enthalpy of water in the liquid phase, the enthalpy of, water in the solid phase. We always have to define it as a change, as a chemical reaction. And so that's why we've defined these standard enthalpies of formation to have a standardized type of reaction that we're referring to. So again, this is a standard enthalpy of formation. This not means it's at standard state, and the F means formation. And it is the enthalpy change of 1 mole of an element in a standard state to make up the chemicals of interest. So that means my stoichiometry here in front of my element, this is my standard enthalpy of formation of methane gas. My stoichiometry always has to be 1 here. And then I'm making it up of the constituent elements in their standard states, in their standard elemental forms. So for carbon, that's this solid graphite. And for hydrogen, that is hydrogen gas. Okay. And so we've got tables and tables of these values that we can look up and then see here are some examples. And here we have a general reaction, right, that we're talking about. So my enthalpy of reaction is defined as the sum of the enthalpies of formation of my products minus the sum of the enthalpies of formation of my reactants. Okay, now a couple of things, and here's sort of my generalized equation, right? So here are my products, here are my reactants. Now, here are a couple of things to notice from the table here. First of all, my O2 gas, you'll see that my enthalpy of formation is 0, right? So it turns out, so for all of these standard enthalpies of formation, I can write an equation for them, right? So for water, I'm forming 1 mole of water in the gas phase. That's going to come from half O2 in the gas phase. That's because I know oxygen in its elemental form is O2. I only need one atom of oxygen, so I have to divide O2 by half plus a mole of hydrogen gas, right? Now, if I was defining that for O2 gas, my product has to be O2 gas, but what is O2 in its elemental form? Well, it's O2 gas, right? So by definition, the enthalpy of formation for anything in its elemental form is always 0, okay? The enthalpy of formation is 0. That's by definition because it's basically a not reaction. The reactants are the same as products. The other thing I wanted to mention here is you'll see we have liquid water here and gas phase water, and they're not exactly the same, right? And we'll see that the enthalpy of formation of liquid water is more exothermic, right? This one is more exothermic than the enthalpy of formation of gas phase water. Does that make sense? That there would be more energy out? I'm forming both of them by its constituent elements, but I'm getting even more heat energy emitted when I'm creating liquid water as opposed to gas phase water. And this is because I have increased intermolecular forces, right? So this is again going back to the fact that the states of matter are important here, right? Because intermolecular forces, it's always an energy out to break intermolecular forces, an energy in. It's always an energy in. It takes energy to break intermolecular forces. So we'd have a positive delta H and energy out to form them. And I'm forming more intermolecular forces in the liquid water than I am in the gas phase water. Okay, so I'll pause for a minute. We only have one more topic to talk about. Are there any questions that have popped up, Hiba?
Yeah. So what would we do if something is not at standard state?
Okay, so that's a great question. So then we can't use the not. So basically what we would do here is if you want to use standard enthalpies of formation, you are by definition determining the enthalpy of the reaction at standard state. And then often actually, so this will be something you'll talk more about when you do thermodynamics again at the end. Often when we actually make some changes to the reaction, we're not actually necessarily going to change. The enthalpy isn't going to change that much, actually. So sometimes we will have things that say, assume the enthalpy at standard state is the enthalpy in the actual reaction, right? Because obviously we can't stay at standard state all the time if we have a reaction going on, because some things are going to go higher than 1 mole or 1 atmosphere or lower, right? We can't stay at standard state forever. And so often we would say that, assume the standard state enthalpy is the same as the enthalpy of the actual system. I think this will come up even more when we do a new thermodynamic constant, which is Gibbs free energy, where standard state actually becomes even more of an important reference point than it does for enthalpy. But I would say you're not, if we use the heats of formation, you are by definition calculating the reaction at standard state, but often it applies beyond that. Yeah. Is there another question, Hiba?
Yeah, like a couple of questions asking the difference between the delta H for water, liquid, and gas.
Yes. So I'm just trying to emphasize the fact that the reason, so the reactants in both of these cases are actually the same because they're always going to be their elements in their standard state. The only difference is whether my product is in the gas phase or my product is in the liquid phase. And the fact that in the liquid phase, I see it as a more negative number means more heat was released, forming liquid water from its constituent elements than when it was formed and it became a gas. And that's because of the extra heat released, heat out, when I form those intermolecular forces between those water molecules. Okay, I hope that helps. Let's do our last topic and then we'll come back to more questions. I really appreciate all these questions. Okay, so the last thing we're going to talk about is another way to calculate enthalpy, but this is not, so these standard enthalpies of formation, those are actual ways to calculate actual enthalpy values. They're quite accurate. So these tables are very reliable. Here, we're talking about a way to estimate enthalpy values. It can be useful when you think, what do I think is happening here? But they're not reliable to calculate very accurate enthalpies. And that's using bond energies. So in this sort of paradigm, basically what I'm thinking about, if I have a certain energy of my reactants and a certain energy of my products, basically I'm taking all of my reactants and I'm acting as though I've broken all of the bonds of my in my molecules. And then I've taken those same atoms and I've allowed them to react and become products. It gives me an estimate of whether overall my reaction is exothermic or overall my reaction is endothermic, right? So the example here says in methane, what I would do is I'm basically breaking 4 carbon-hydrogen bonds. That's the up here. And then what I'm ending up with is some of my carbon stays on its own, right? And what I'm forming, so that this is the reactants, I'm forming carbon and hydrogen, right? So that's my bonds breaking. And then I would have them reforming to give me something else. Maybe I would have an actual reaction here, right? So going to CO2 or water or something like that. Okay, so there's an actual problem on the next slide. So let's go to that and talk about the practical application there. There is sort of general trends in bond energy related to atom size and the length of the bond. So generally speaking, a bigger an atom or bigger atoms form longer bonds, and both of those things make for weaker bonds. So the longer a bond, the weaker it is, and often larger atoms form longer bonds, making them, by definition, weaker. So this is sort of the first part of this is what it would take to break those bonds. Now we have to think about the energy out if they went on to actually form into something else. So here's our example. And our example is to estimate the enthalpy for the formation of hydrochloric acid from the reaction of chlorine and hydrogen gas. Right? So here, again, this isn't equal to, it's an estimation. So in order to estimate that, we need to add up all of the bonds broken in the reactants. So the bonds that were broken in the reactants are a chlorine-chlorine bond, right? So we're breaking a chlorine-chlorine bond. So that will take 243 kilojoules per mole of energy. We're also breaking a hydrogen, that's the chlorine-chlorine. We're also breaking a hydrogen-hydrogen bond, right? So generally speaking, we have to put in about 436 kilojoules per mole to break that bond. Now then we subtract, so that's our going up. That's why we're adding. Now we're going to subtract our bonds formed, right? So our bonds in our products. So in this case, it's 2. So that's why I have a minus here. Minus 2 times the strength of my hydrogen chlorine bond. Okay, so again, this is an estimation. This is my reactants, and that's my products. So overall, this gives me an estimated enthalpy value of about negative 185 kilojoules per mole. So this is an estimated enthalpy value, right? So we can use these to sort of get a sense of whether overall does the reaction seem to be exothermic or does the reaction seem to be endothermic? All right. Any questions about this?
I just got one.
Mm-hmm.
How do we distinguish standard enthalpy of formation from bond energy?
How do we distinguish what enthalpy of formation from bond energy?
Yeah.
Yeah, so the enthalpy of formation, those are tables of values, and those are quite accurate. Like these are, they're quite reliable. They're based on experimental values. There's huge databases operated by with high quality control around the world to measure these things. And so these are very accurate, actually. But using bond energy to estimate enthalpies is just an estimation. Because again, we're talking about, especially when we're looking at things like bonds to chlorine, molecules, the bond energies in a specific molecule is more complicated than just these generic tables, right? And so it's not really it also isn't taking into account intermolecular forces. So this is just an estimation. This is an estimation, but the enthalpies of formation are much more accurate. So there's one last slide left in this slide deck, and this is just a overview. Okay. So the overview here is that we started with the idea of internal energy. That's all the energy in the system. So our delta E is composed of both of heat and work, right? So they can be the delta E is a state function, but the amount of that energy that ends up as heat and work is a path function. We also talked about the fact that the energy of the universe isn't changing, and so this is sort of our basis of calorimetry, where the change in energy of the system is equal to the negative the change in energy of the surroundings. We defined the idea of enthalpy, right? And then we also talked about the fact that we measure enthalpy, and really functionally speaking, enthalpy is the heat exchanged, so consumed or released at constant pressure. And when we're talking about calorimetry, the heat exchanged or released or consumed at constant volume is a direct measurement of delta E. Okay, so delta H is measured when we have constant pressure, delta E is measured when we have constant volume. And in today's lecture, we talked about some applications of Hess's law, which is the fact that we can add enthalpies when we add reactions, and we can also use things like heats of formation to predict enthalpy changes at standard state. Okay, so I think that's all of our actual content. I might want to go back to that question that before we leave, or we see if there's other questions. Let's go back to that question we had at the beginning that I couldn't quite nail down, because I want to make sure, especially if I misspoke or if something wasn't clear last time. Can you say that question again, Hiba, that we were struggling with? Can you try to go back to that?
Yeah, I will try to find it.
Okay. Is it related to this?
I'm not sure.
Okay. Well,
It was talking,
yeah.
yeah, it was talking about like delta E and delta H, difference between both of them.
Yeah, I mean, delta H is basically delta E minus work, right? Because work is equal to negative P delta V, right? And so when we add we add P delta E, we're basically subtracting work, right? So basically, when we measure heat at constant pressure, we're measuring enthalpy because it is the heat exchanged, but it doesn't account for the work done by any gases that might be present or had work done on them. Okay, well, let's just see. Are there any other questions, Hiba, from this lecture that we should address before we move on to office hours?
Yeah, I just got like a couple of questions asking about
Sure.
the tables
Yeah.
value, if they're gonna be provided on the exam.
You mean like these types of tables or the heats of formation?
Yeah, both of them, yeah.
Yeah, I mean, you wouldn't be expected to memorize them. So you'd either be provided with the specific values you needed, or you'd be provided with a table. You wouldn't be expected to remember them. Yeah. Except for you would be expected to maybe remember that the heat of formation of an element is 0. That you might be expected to remember. Yeah. Is there another question, Hiba?
Yeah, I think there's a question related to like how to calculate the delta H based on the bond energy. So the question
Yeah.
is, do we only do this method if the question clarify to use this? Otherwise, we would use Hess law or standard enthalpy of formation.
Yeah, yeah, yeah. This is just yeah, you would only do this if asked to do it this way. Typically, it would be pretty clear which mechanism you would be expected to use in the question, I think. Yeah. But if you had to choose, you would definitely use the heats of formation over this estimation technique. Yeah.
Yeah, why is delta H for single oxygen endothermic?
Okay, is that talking about in this table? Like, is there an OO? So one of the things to think about is all the bond energies are endothermic, and that's because breaking a bond takes energy, right? So the bond energies, we're pulling them apart. So all of these bond energies are by definition endothermic, because that's what we're defining here is breaking a bond like that. I'm not exactly sure what you're talking about there. Whether it's
I
referring
think
to the
this
Z.
one. Yeah, I think
Oh,
this
this
one.
one up here.
Yeah.
So that's actually forming gas phase oxygen atoms. So that's actually over here, we have a lone oxygen atom. And so that would actually be being formed by 1/2 of oxygen gas. And actually, so that would be an endothermic process because we're breaking that O2 bond to get just a lone atom. And this is, I mean, so again, it's interesting to think about. This is not a reaction that probably is favorable on the right-hand side, but it's not an impossible reaction. It's actually, there's quite a few oxygen atoms. I would say oxygen atoms play actually an important role in the chemistry of the atmosphere. So it is a reaction that is something that's important to discuss. All right, well, we're at 8 o'clock. I just want to thank everybody for being here. Hiba, can you go ahead and stop our recording? Goodbye.